This is Mec382, Challenge 4, Quality Management System. The task of the system is to relieve the operator of the task of searching through bins and spending time verifying the circuit board's accuracy by hand. This both consumes time and can become a physical strain due to repetitive motion injury of searching through the bins and holding the same position. In the current process, the operator takes the circuit board out of the randomized bin and verifies if the circuit board is missing any components. If the board passes, they place it into a bin of passed parts. The failed pieces go into a separate bin of failed parts. In this video, you can see my classmate Sam operating the machine vision system. Both the future system and the current system are in batch flows, and this would operate on the same principle. The future system does have very close tolerances, with only a shift of 5% or more in the part causing an error due to the technique of basic frame differencing, which saves an image and overlays the current snapshot over the image and compares their difference by a percentage being the solution chosen. This made fixtures an important element of the design of the system. Bringing in another fixture to accompany the camera stabilization fixture is the circuit board fixture, which holds the piece snugly in place and prevents the object from shifting to create an image that doesn't include motion, so the missing parts are easy to contrast. This makes their missing components appear as motion in the frame. Backlight also proved to be an important player in this vision system, with the parts containing just enough transparency and variation in elevation of parts that the tops of the components contrasted the base of the circuit board, allowing the camera to recognize the individual components more successfully, with the addition of backlight in comparison to overhead light. What we used to create the backlight was by placing the two LED undercounter lamps that you see into the box and lining the box with a 12-inch run of LED rope lights to further illuminate the part. This is all shining through a piece of fogged acrylic to secure the fixture, allow the backlight to shine evenly through the circuit board, and diffuse the light. Take notice in a moment when my classmate opens the door on the vision system in the part presentation. This remains the same through the entire test. The part is placed towards the operator at all times. This is due to the system requiring a standardized orientation for the basic frame differencing to capture a difference in the frame. For the circuit board to pass, it must be facing in the position that the template of the sample boards was placed in. In this case, that was with the relays towards the operator in the bottom left corner if peering into the light box. As you can also see from my classmates' interaction with the vision system, this system contains a human-to-machine interface and will require the operator to carefully place the part into the fixture, close the door, and press the button to take a snapshot. It will also be the job of the operator to maintain the system by removing any debris inside the light box and maintaining and replacing the camera lens when needed. The requirement for the light box was due to the vision system's sensitivity to ambient light and the way it recognizes objects. The light box isolates the environment and allows the image produced by the camera to become more stable. The light box also serves as the housing of the camera and allows the camera's stabilization fixture to be mounted. The current manual process has a 90 to 100% accuracy level, and this vision system under controlled circumstances can serve at this level of accuracy. The time that this vision system takes to process the circuit boards also meets or exceeds the current speed of the operator, while making less decisions and motions for the operator. The camera system used for this application was the OpenMV H7 with a QVGA 320 by 240 pixel resolution to capture the image. The maximum part size was 2 inches in height by 3 inches in width, which made the distance for the field of view need to be at least 5 inches from the camera and possess a 72-degree field of view to capture the entire circuit board. The circuit board also has been risen to capture smaller components on the circuit board and allows the distance from the camera to be adjustable. However, this doesn't defeat the system's overall portability, with this fixture being able to be quickly secured into the image sensor's field of view. The mechanical portions of the system are the two fixtures mentioned prior in the video, and the light box itself, which is a 10 by 10 inch ductless light box that has a reflective interior allowing for even light reflection. This light box has an average lifetime of 40,000 uses and requires replacement if excessive wear and tear occurs. The electrical design of this system involved very few parts, which were just the button, which was signaled from pin 6 on the OpenMV, and then also grounded to the OpenMV. The other electrical devices involved were the rope lights shown prior in the video, and the LED lamps that are rechargeable by the same USB 2.0 port that accesses the software from the laptop to the OpenMV. The cost of the project, as you can see from the table, would involve the initial cost of the items that are necessary to start using the vision system, their lifetimes, and some of the items to maintain the system are listed. The price in the cost column is the price of products to start. To the right of that is the average maintenance cost after 3 to 4 years or when lights need to be replaced. This OpenMV itself starts out at $70, and the total startup cost includes the operator's first month's salary is listed, making the total startup cost $3,339.96. Some items that are more maintenance costs are the OpenMV lens, the light box itself, and the 3 lights that are included. The software that the OpenMV utilizes is the open source OpenMV IDE that can be programmed using Python to complete various computations on the OpenMV, like this very project. This leads us in to the program that was used to complete this project. We start on part 1 of this 2-part code by first importing libraries. Then we check how many frames were printed before blending, and then we blend by this amount. We initialize the camera sensor, and we change the pixel format to RGB, and we change the resolution to QVGA. We skip 2000 frames, and we also set the white balance to false, and we set the auto exposure to false. And then we set the auto exposure to 120,000. This prevents light variation at the beginning of the program, like globally. And then we initialize pin 6, and we assign it to shutter, and then we create a function called capture color threshold. And this captures a 50 by 50 pixel squares in ROI to find the bead channel color value. We take an image and assign it to a variable called image, and it sets a variable to pull the data from the histogram. We get the CDF of the histogram at the 1% range, and we get the histogram at the 99% range, and we set a variable of the sum, high and low. We return the threshold variable, and then we set the variables for the color thresholds, and this changes depending on the image that you're getting and the exposure. This was able to make more stable thresholds. And then we check if the template directory exists, and if not, if there's no template, then we make a template. And then we go into the while loop, and we take the color threshold function and assign it to color threshold. And then we make an if statement for the button press. And then if the threshold is met, we set the exposure off and set the exposure to 120,000, and this determines that the color's blue. And we take the snapshot, we take the snapshot then, and we apply it to the image. And then we save the image as a blue image, and we print that we save this color. continue doing this for all of the different colors, gray, red, yellow. And then, as an else statement, if these color thresholds are not met, we print color not recognized. And then there's a time delay of 1 second to prevent multiple images. And I did not realize you couldn't see this if statement when I was explaining it. But if the color threshold is met that we set when we're not pressing the button, then that condition is met and we set the auto exposure to 120,000. And I'll explain in just a moment why we set this again. But we take a snapshot and we assign it to image, and then we save that image as temp/blue. So we're saving the image, and then we're going to print that we saved a circuit board of blue color. And we're going to do that the same for red and yellow. But for gray, because of the transparency is a little different, we had to increase the exposure to 400,000 to get a clear image. So we save gray, but everything else is the same. And then for the else statement down here, we take a snapshot. And this is when we're not pressing the button. This is the counter to this if statement. And then we print the color threshold. So what we're seeing currently, it gives us a good idea of what we can set our thresholds as. And then there's a time delay. For the second part of the code, we do the same. We import the libraries and we initialize the camera. And then we also assign pin 6 to the shutter. And then we also do the capture color threshold function again. And we return the threshold variable value. And then we also make the function diff value, and we declare triggered as a global variable, and we initialize triggered as false. We set the threshold for triggering the difference to 5, and then we set the number of frames to 50, and we blend by 256, and then we initialize the frame count to 0. We then check if the frame count is greater than BG update frames, so 50. And then if it is, and it's triggered is also false, then we enter this if statement and we reset the frame count to 0. And then we blend the temp file name that we gathered earlier. So this will be the file that we gathered from the picture. And then we're going to save that image. And then we're going to see the difference between the two images. And then we're going to set a variable to pull from the data from the histogram and assign that to histogram. And then we're going to do a get percentile value of the L value minus the get percentile of the L value low percentile. And then we're going to take if the difference is greater than the triggered threshold and assign that to triggered, and then return triggered. Then we're going to set the variables for the color thresholds. Just like the last program, it's going to be the same. These are going to mimic the last program. And then we're going to set the frame count to 0. And then we're going to enter the while true statement, and we're going to call the function color threshold and assign it to color thresh. And then we're going to take an image and assign that to image. And then we're going to iterate the frame count by 1. And then we're going to enter the if statement for the button press. And then we're going to, if the color threshold of the red board meets the color threshold again, we're going to set the auto exposure to 120,000. And then we're going to check if the difference of the red value is 95% close. As you can see, some of these have different percentiles, and that depends on how close of a tolerance you want for your frame differencing of your difference value. This is the same for all of the colors again, except for gray. We change it. And then once again, the percentile difference that the shapes can be. I mean the circuit boards. And then if triggered equals false, we draw the pass or fail on the top right. I don't know if you can see down here. Try to grab that area. So right here we're going to draw the pass or fail. So if triggered equals false, we're going to draw pass. Otherwise, it's going to be a fail. And then the sensor resets, and then there's a time delay of 2 seconds. And then if the button hasn't been pressed, we're going to be taking pictures continuously still, printing the color threshold with a time delay. So we can gather these color thresholds again to make sure that they're still stable. And that is everything for the code for this project. Thank you for watching.